Hello dear students, today we are going to study the eye as an optical instrument. Let's start with some theoretical notions. The diopter represents a surface that separates two different transparent media. If parallel rays of light meet a plane diopter, by refraction they will be deviated, emergent rays remaining parallel. But if a beam of parallel rays passes through a spherical diopter, the beam becomes either diverging, either converging. The lens is a piece of a transparent material, delimited by two diopters with regular surfaces, of which at least one is spherical. They can be converging if they bring together the rays of light, or diverging if they spread them. Lenses are characterized by the focal distance. It is defined as the distance between the point of convergence or the focal plane and the lens. For converging lens, the focal distance is positive and decreases the more bulging the lens. For diverging lenses, the focal plane is obtained by prolonging emergent rays. Thus, the focal distance of a diverging lens has a negative value. The convergence is defined as the inverse of the focal distance. Thus, diverging lenses have a negative convergence. In its three parts, this laboratory work proposes to you to visualize the path of light rays when meeting different optical elements, prisms, lenses, mirrors. To identify the four diopters and the four transparent media in the eyeball. To study image formation for the emmetrope eye and also for the eye with different refractive errors. For this laboratory work, you will use the geometrical optics kit containing prisms, lenses and mirrors, and a light source providing four parallel light rays, an anatomical model of the human eye, a functional model of the human eye containing an optical bench with four mobile stands, convergent and divergent lenses, and a light source on the optical bench. Plug in the light source to obtain the parallel light rays. Use the optical elements as specified in the worksheet and place them in front of the light beam. Draw on the worksheet the path of the emergent light rays for each optical element. Explain why the direction of the light changed and specify the physical phenomenon for each situation. For the second part of the laboratory work, disassemble the anatomical model of the human eye in its composing parts. Identify and name the four diopters and the four transparent media in the eyeball. Write in the table their names in the order in which the light passes across them. In the third part of the laboratory work, we will try to better understand the causes and the correction for the most important refractive errors: myopia, hyperopia, and presbyopia. First, we will study image formation in the normal or emmetropic eye. For this purpose, we will create a model inspired by Listing's reduced eye model. The symbols on the rail of the optical bench have the following significance: N, normal eye; M, myopic eye; H, hyperopic eye; and P, presbyopic eye. To simulate image formation in the emmetropic eye, place the light source next to the letter N on the right side. This way, the light source acts as a light object for close view. Choose from the kit the lens that simulates the accommodated crystalline for close view, the thick biconvex lens, and place it in the holder of the anterior hemisphere of the eye. Place the anterior and posterior hemispheres next to the corresponding N letters. Describe the image on the matte glass screen on the posterior hemisphere. You will now study vision for distant objects. Choose the lens that simulates the crystalline accommodated for faraway objects, the thin biconvex lens. Place the holders in the same positions and replace the lens simulating the crystalline. Compare the image you obtained previously with the one in the new conditions. Remove the light source and its holder and orientate the optical bench towards faraway objects, like trees and the tower of the cathedral. Describe the image you observe on the screen. Compare the curvatures of the two lenses and draw a conclusion regarding the changes of the curvature rays of the crystalline while adapting with distance. To study image formation in the myopic eye, place the holders for the anterior and posterior hemispheres as well as for the light source next to the corresponding M letter. Place the lens with maximum convergence in the holder of the anterior hemisphere. Look on the screen and observe the formation of a blurry image. Place the holder imitating eyeglasses next to the corresponding M letter and insert the correction lens. Look at the screen and check correction of image. In the case of myopia, the antero-posterior axis of the eye is longer and the clear image is situated in front of the retina. Crystalline convergence is not adapted to this situation. To bring the clear image on the retina, decrease the convergence of the optical model using the correction with the divergent lens. To study image formation in the hyperopic eye, place the holders for the anterior and posterior hemispheres as well as for the light source next to the corresponding H letters. This way, the antero-posterior axis of the eye is shorter comparing to normal eye. Keep in the holder of the anterior hemisphere the lens with maximum convergence. Look at the screen and observe the formation of a blurry image. Place the holder imitating the eyeglass next to the corresponding H letter and insert the correction lens. Look at the screen and check image correction. For the hyperopic eye, the antero-posterior axis of the eye is shorter and the clear image is situated behind the retina. Crystalline convergence is not adapted to this anatomical situation. To bring clear image on the retina, decrease the convergence of the optical model using correction with a convergence lens. To study presbyopia, bring the hemispheres in the positions corresponding to the emmetropic eye. Replace the crystalline with maximum convergence used previously with the one with smaller convergence. Presbyopia is not due to geometrical abnormalities of the eyeball. It is caused by a reduced elasticity of the crystalline, who cannot bulge accordingly for close objects. Look at the screen and observe formation of a blurry image. Place the holder imitating the eyeglass next to the corresponding P letter and insert the correction lens for presbyopia. Look at the screen and check image correction. In presbyopia, crystalline convergence is reduced by comparison with the normal eye due to its reduced elasticity. To bring the convergence of the optical model to normal value, apply correction with the convergent lens.